All right. Hello, everyone. Welcome to my ASME workshop. This is 2.5 axis CAM with Solidworks CAM. And so I'm just going to teach you or go through the basics of setting up a part in SolidWorks CAM and making some kind of simple features with it. Setting up a tool crib and machining, saying your machining parameters, and then exporting it or post processing it to a TXT file or G code file that then you can use in a CNC machine. So, before that, I prepared this little PowerPoint to go over some of the terms you need to know. So, first off, is why am I saying 2.5D instead of just like 3D? Well, it's kind of just like a classification of operations with CNC machines. So 2.5D machines are things that all go to a level surface, as in you're plunging into a part and it's going to just terminate at one flat surface. It's not going to go like at all these different surfaces. Basically, it's going to have a flat surface instead of a curved surface on the bottom. So this involves pockets, slots, holes, engraving, really simple operations. Um, 3D operations in a CNC means curved surfaces, like I said, or um, like a airplane blade or something. And these you use usually ball end mills to do that, and these end mills leave scallops. So then there's like an extra element of like when you do your step overs in 3D operations, you have to keep into account the scallops, and there's usually some sort of finishing step that has to be done afterwards as well. But for now, we're focusing on 2.5D, which is seen in the top picture. That's a classic example of a 2.5D part. Those slots and stuff are curved, but the bottom of them is just perfectly flat or all the way through the part. Um, the one on the bottom is a 3D operation. As you can see, it's a bunch of curved bottom surfaces, and it's using a ball end mill. So in addition to that, there is math involved in machining besides just measuring things. So CNC is an automatic machining center, basically. So you put a program in and it follows that program. Well, the numbers it knows to follow its feed rate, how fast it's going into the part, and its spindle speed are actually determined by formulas. So the first little formula I have here is just 12 divided by pi equals 3.82. And this is just kind of like a constant because in the following formula, where we determine our spindle speed, we're using something called surface feet per minute. And we're just converting that surface feet per minute to inches because the diameter of the tool is usually in inches. Surface feet per minute, as you can see, is in feet per minute, is it's an experimentally found number, but it's basically just how much is optimal to feed into the material in a linear sense of a foot. So if you're like a straight line into a tool of that material, um, what is the optimal feed rate of that uh, material? So it's, like I said, experimentally found. So there's not really any way to estimate this, and it varies significantly between materials. And even within a material, say like aluminum, it can vary significantly between, say, T7062, which is like aircraft grade aluminum, and T6061, which is like just general purpose cheap aluminum. So those have dramatically different surface feet per minute feed rates, and it's usually like a range, but sometimes they'll give an exact number. And this is very important as it determines how fast your tool should be spinning when you're machining. And that in turn leads into the third equation, which is the calculation of the feed rate. So the feed rate is just the revolutions per minute, the spindle speed, times the chip load, which is how thick your chips are in inches in this case, times the number of flutes on your tool. So flutes are cutting edges, basically. Flutes are actually the grooves in which chips collect in your cutting, but there's the same number of those grooves as there are cutting edges. So you just count the number of edges. Um, the number of flutes has an influence on how fast you can feed into it because more cutting edges you can cut more faster with less of a rotation. But going back to the chip load is, like I said, the thickness of your cut. Every time you do a little turn, each flute is cutting a specific thickness of chip because the feed rate is completely even. So this usually varies between 1,000th of an inch and 5,000ths of an inch. So this is like a finishing pass is 1,000th, and a very large roughing pass would be 5,000th. Um, Usually somewhere in between is like general purpose pocketing or feeding. So I think in this case we'll be working with 3,000ths of a chip load. So, and then your feed rate is in inches per minute or IPM. Sometimes it's written IPM. And it's just the speed of your cutting tool, like I said, just how fast you're going into the material to cut it. And so, just these three simple equations will, particularly, we want to look at the surface feet per minute one because RPM has a huge impact on your machining. Basically, it can make the difference between breaking an end mill or melting your material. Uh, so these formulas are for milling only. There are like kind of adaptations of these formulas. They're slightly different that are used for lathes. So if you're turning your part or if you're facing your part on a lathe, it's a little different formulas. But for milling, these are the three formulas. You can look these up and they'll pop them up. Just put like RPM formula milling and you'll get this same equation, and feed rate milling formula and it'll pop up this. So other than that, with milling, there's two types of milling. There's conventional milling, which is seen here in the figure 2 picture. And what you're doing basically is you're rotating and feeding the cutter in a way such that when it makes a chip, it's starting at the smallest point or a theoretical zero, and then getting to the largest point of the chip. So the real thickness of the chip right there. And what this does is it usually results in kind of a worse surface finish than the other method, which is climb milling. It results in the cut chips. If you look at this bottom picture, they get thrown in front of the cutter again. Um, so they'll go back in front of the cutter and just get kind of reground. So that makes evacuating chips an issue, and that can really diminish surface quality and your cutting rate, and it'll increase tool wear as well by doing that. So, but a major thing about this is that the tool deflection is parallel to the cut. So if you can look at this, the conventional milling, like all of its load is in line with the way it's being fed. This fed arrow is like kind of backwards. Um, but it's that the thickest part of the chip is going to like push back in line with the cutter. And so what that means is that you're not really going to have uh, this accuracy. Your tool is not going to cut deeper into your part, basically. So you get more dimensional accuracy, like with regards to the profile your tool is cutting. So conventional milling, despite like it increasing tool wear and resulting in worse surface finishes, is used in micro machining, like making extremely small parts like watch parts, because it allows for a much finer accuracy. Uh, Even if it does have increased chatter when making larger cuts, when making extremely small cuts, it is much more accurate than climb milling, which climb milling, when making larger cuts, is actually has reduced chatter and results in finer surface finishes by extension. And it gets the chips out more efficiently from your cut. As you can see uh, by this picture on the right side, it's really just throwing the chips behind the cutter, and it should be feeding the other way than where it says it's gonna. Or I'm sorry, this feed arrow is with respect to the part, so like the part is moving, not the cutter. But yeah, so the chips get thrown behind the cutter. This results in better heat dissipation, better cut, better pretty much everything. But like I said, really only large scale things, which is what we'll usually work with. Micro machining is a completely different beast. It uses completely different tools, completely different designs as well. Um, but yeah, so pretty much all of the operations we'll do today will be climb milling, and you don't have to do this kind of rotational feed related math in your head. SolidWorks just has a little check mark. You can check for climb or conventional milling for the operation. So yeah, that's it for my little presentation. Let's get into the part. So this is the part I kind of gave everyone. Uh, it's a pretty simple part. Uh, it's just got surfaces that would be kind of hard, or well, several surfaces that would be impossible to machine on a conventional mill, like this curved surface. You could make this part on a conventional mill, uh, but you could do it a lot faster on a CNC. And this circular pocket here, uh, can't really do on a conventional mill unless you just drill it, ream it. Um, and then this little kind of uh, slot runner thing is just a simple ball mill thing. But I made this kind of weird part just to go over several operations SolidWorks has for CNCs. So we'll try and cover as much as possible with just one little part. Let's get into it. So the first thing you need to have is your SolidWorks CAM tab, which if you don't have that, you just go to your tools and then add-ins, and then you would just check SolidWorks CAM, whatever year you have, and then you click OK, and it'll take a while to load in. But once you have it, you can begin. So on your little task pane on the side, SolidWorks, the CAM module will add these three tabs at the end. And so what this is like your stock manager, your uh, operation tree. Sorry. Uh, so this is basically your machine and your operations, and then this is your tool crib. So this has all the tools you want to use. So we're going to start first by specifying our stock material. So a machine, if you double click on that, you can change it between a regular mill, which is what we're going to use. And I just clicked right here on the machine in the feature tree tab. Uh, you can choose between that, a 4-axis, a 5-axis, or a turning machine. Um, then you can specify your tool crib. So we're actually going to want to change this one. You should have 3 default tool cribs. One of them is right now we're in 2, tool crib 2, which is just a general tool crib, and tool crib 3 is another general tool crib. What we want to do is change to tool crib 1, which should be empty. So if we select it, see, we are now empty. All I did was click tool crib 1 and hit select. And we're going to want to add our own tools to this tool crib. So the ones we're going to want to add, we're going to hit add tool here. and we get this little pop out. And so first of all, tool type, we need a drill to make these holes. So we're gonna go to, in the tool type, just drop down arrow, the second one, drill. And we have a huge list of drills. I saved us some time by noting the number of the things we need. So we need 106 drill. I'm going by this like ID number that SolidWorks assigns. So 106 is right here. It'll kind of like show you the little drill right here. Um, this is a 1/4 E drill, so it's a 1/4 inch drill. 1/4 and E in drill sizes are the same thing. Specifically, it's a CNC drill, so it's got kind of a wide taper. CNCs go really fast, faster than conventional mills, so they can. Tools are usually designed different for them, including especially drills. Um, so we're gonna have that one selected. See it's selected in black. We're gonna click OK and see. Now it's in our little tool crib. So we're gonna do that again, and we're gonna go to flat end mill. Where's just regular flat end mill? Oh no. Oh no. We don't want a flat end taper. Oh, it's right here at the top. Third one from the top, flat end mill, which is, this is just a square end mill, a regular end mill basically. And we need three of them. We need 30, 44, and 52. So let's go to 30. It's a 1/4 inch end mill, two flute. Uh, yeah, we need two flutes. This is going to be aluminum, which I'll show you how to specify the material in a bit. Uh, so two flute end mill, we click OK, add tool. We're going down to 44, 3/8 carbide end mill, two flute again. We're going to click OK. And we're going to go add tool again. We're still in flat end. 52, 1/2 inch carbide end mill, two flute again. Okay. Then we're still adding some more tools. We're gonna add two ball end mills. So
Sorry,
yeah,
what was the last one?
the last one for the flat end mills was 52. Uh,
52.
yeah, it should be 1/2 inch two flute.
All right, thank you.
Yeah, let me know when you have it so I can. Yeah.
I got it.
Okay. All right. So we're gonna go to add another tool. Instead of flat end, we want ball nose, which is fourth from the top of the list. And so ball nose just has a rounded end, a perfect like half circle end. And we want number two, which is a 1/16, very small end mill. Gonna click that OK. And we want still in ball nose, we want 25, which is 1/4 four flute. Actually, we don't want four flute. So the 16 one we got was two flute. We don't want four flute. That's way too many flutes for aluminum. Uh, it's going to melt and clog up the, even if you go slow, it'll melt and clog up the end mill. And then you just kind of ruined a perfectly good end mill. So we'll go with 26 instead, the two flute 1/4 inch. And okay. All right, so this is our tool crib, kind of a weird tool crib. And you can kind of move these around. You can edit the tools as well while you're here in the tool crib, but we'll come back to that later because we do need to change some of these tools. You can make your own tools in it, but it's also a lot easier to just edit these tools. And editing these tools in your tool crib doesn't change their like where we pulled them from. So you don't have to worry about like, oh, I just permanently changed a default tool kind of thing. Like that's these tools are just localized to your little thing. So post processor, we won't worry about that right now. Setup, rotary axis, tilt axis. This is for
One question.
yeah.
So in the two, three, how do you remove one? If you make a mistake, how do you remove it?
Right here, if you
Okay,
select one of them, there's a remove tool right here next to edit tool.
yeah,
And
thank
yeah,
you.
yeah. So yeah, that's a good question. Um, like I said, this rotary axis and tilt axis tab is for 4 and 5 axis machines. So we're not going to worry about that. So that's pretty much everything with regards to our tool crib. Again, we'll come back and change the tools in a little bit. So we'll click OK. This, oh, actually, oh no, what happened? While I'm here and my thing's kind of frozen, this medium duty, you can change it to like high duty or low duty. It doesn't really make a difference. It's just kind of like the maximum parameters that SolidWorks is rendering to for the machine. So if you're using an extremely industrial heavy duty high speed milling machine, then by all means put it to the max. But we'll just go with medium duty for now. So right beneath the machine, uh, in our little feature tree here on the left side, is the stock manager. So if we double click that, SolidWorks is usually pretty smart. Uh, it'll kind of recognize for you, uh, like just the general outline of your shape. That's your stock. You can change it. You can add or subtract from the X directions and the Y and the Z directions. Usually you would do this because you'd be cutting from something larger than your stock to get these perfectly flat faces. But for now, we'll just leave it like that. We'll focus on just making these contours for now. So it should have already selected. Here at the top is material. And material, we do want the 6061 T6, which is just regular, like run of the mill aluminum. 6061 is like the most common alloy. And T6 is a heat treatment. I think they just like, after it comes out of the furnace, like air cool it or something. But there's a lot of, or it's not really a lot, but it's kind of like the most common materials. It's even got polymers, it's even got exotic materials. There is a massive database which you have to like search for, but you can add even more materials in here. And when I say massive, I mean like it slows your computer down, and that's because I have a good computer loading just how many materials they have listed. So what this does is it kind of makes SolidWorks get its default surface feet per minute. Remember I mentioned that, and the feed rates, they're all tied to these materials. So selecting one will kind of get SolidWorks default for that material. But I'm going to show you how to input them manually as well, because SolidWorks default is not always optimal. So yeah, 6061 T6, that sounds good. Um, you got a question, one more?
Yeah, just how'd you get there again?
The
To
stock manager.
SolidWorks.
So right here, remember these three tabs that
Mm-hmm.
came up at the end?
Yeah.
Uh, yeah, this one, the CAM feature tree, and then machine. Or if you're on the SolidWorks CAM tab, I think it's define machine. And no, that's no man. I'm sorry, it's a stock manager right here on the SolidWorks CAM tab. You can just hit stock manager,
Okay. Yeah.
top left, and
Mm-hmm.
yeah. So
And it's
there,
6061 T6.
yeah, it should be the default.
Mm-hmm. Okay. Yeah. Mm-hmm.
Yeah, I kind of tried to keep as many settings to default, so it'd be pretty
Mm-hmm.
straightforward. Um, so after that, we have to define a coordinate system, which is very important because it's kind of what it's basically going to be the zero we're going to set the CNC to uh, when we start machining. So all these operations are going to be referencing that zero. So how do we do it? Well, you can either click up top here on the SolidWorks CAM tab to the coordinate system, or you can just double click here where it says not defined coordinate system and see like a little menu pops up and you pretty much just select a point. So in this case, we're going to go with the top left of our part and bam, you see it spits out a little thing. You want your z-axis to always be pointing up. So in a conventional milling machine, let's say this is the part. It's in the middle of our milling machine bed. So we're facing our part like this, like how it's kind of on my screen right now. Um, to our right is going to be the x-axis positive. In front of us, like going towards the part which is in front of us, is going to be y-axis positive. Right now, y-axis positive is straight up out of the part. It's basically where our spindle would be. So that's not right. We need to change that. So how can we change that? Well, we can click on y-axis right here. This little blank space, it kind of highlights it a little. And then we can click on an edge that we want the y-axis to be on, which is this one. All right. See, the thing is, the y-axis, like I said, positive y-axis is away from us when we're looking at a part like this. So this is kind of backwards. So then we can just click this reverse arrow here on the y-axis and bam, see? And now z is pointing up, which is correct. Up, away from your part is always positive. Towards the spindle is positive, z. So that's what we want. That's our little coordinate system. Well, nice and happy. So yeah, you guys got that? Sometimes if you're just clicking stuff, you'll select multiple things and you'll put stuff for like the Z and it will kind of like conflict with itself and give you an error. So just make sure like you click one line, you make sure it's on the Y, and like it'll sometimes it'll like auto select where you do you want the Z. Just make sure you don't click on another line, kind of like exit that Z option. But yeah, so if ever any of these axes aren't where you want it, you can use that little thing we did, just selecting a line, and if it's not the direction you want, reverse it to get it where you need it. And like I said, conventional milling machine, like CNC, to your right, if you're facing the part, is going to be positive X, and away, like straight the way you're looking, is going to be positive Y. So it kind of always should be like this, such that Z is pointing straight up into the spindle. So we're going to say, okay, check mark that. All right. So, uh, so we now have our tool crib defined. We have our stock defined, and the material, it should be defined as well. And we have our coordinate system defined. So now what we need to do is we need to start defining uh, what we want it to machine. So we're going to go to, in this SolidWorks CAM tab, we're going to go to Setup. We're going to go to Mill Setup because this is a milling machine. And so now it kind of needs, it's asking for a reference plane. And what this reference plane is going to be is it's basically going to be where is the spindle going to like come down on. So right now it's kind of like you want me to come down on the front plane, which we're not going to do like a horizontal milling machine. Let's do a vertical milling machine. So we're going to click just the top surface and see it's already saying like, okay, I'm going to put the tools coming down this way. So yeah, it's what we want. Check mark it. So now that we just have in our SolidWorks feature tree, the CAM feature tree, excuse me, we have this little mill part setup one. You can like rename this and stuff. You can edit the definition and that stuff. But the point is that now we have it, and now we can start defining features we want to machine. Before we do that, I'd just like to point out SolidWorks does have an extract machinable features where it will just kind of auto look at everything and be like, okay, you can machine this, like this, and this, and this. And I'm going to tell you right now, it's really bad and don't use it. It would kind of get what you want to machine, but more so than that, it'll like misdefine what you're trying to machine. It'll kind of like interpret things wrong. Like for instance, this text, it's obviously an engrave. Like I want to engrave that text, but instead it'll be like, nah, bro, this is an open pocket, and you need to like mill it as you would this thing, you know. And it's obviously no, you don't need to do that. So things like that, it's usually, I don't know why did it do that. It's usually just better to like figure it out, like define them yourself, and you can control it a little better like that. So first off, we're gonna right click on this mill part setup in our CAM feature tree, and we're gonna put 2.5 axis features. See, that's where the terminology comes in. 2.5 axis feature. So now this little menu is just kind of like defining features. Like that's all you're doing. So first you need to select a type. A pocket is, um, let's go with pocket first because it's first on the list. So a pocket is like this right here. This is a pocket, this little hole in the center. It's not going through the part. It's kind of terminating before the end of the part, and it's surrounded by material the entire way. So this part on the top, uh, this area that's kind of highlighted, is a slot because it has an opening away, like where the part is just open. Um, so it's not a pocket, but this is a pocket, and likewise, this is technically a slot. I mean, what the hell kind of slot looks like that? But in terms of operation, it is a slot because it has an opening away from the part. It's not completely enclosed by the part's material. So let's start with the pocket. And the first thing you need to do is kind of select, well, what is the pocket? So you can just select the side of the cylinder, and what bam, it kind of highlights it. Uh, this kind of, you can choose like edges, you can choose surfaces, you can choose drawings, which I'll show in a second. But for now, like just for this little operation, we just need to select that surface. Then we go to end condition, which is this little like next arrow, end condition. And so it kind of saw like, okay, that's the contour you want me to make, you want me to define, but how deep do you want it to be? So it's usually defaulted to blind, and for some reason defaulted to this random number. We don't want that, so you can put up to stock, uh, which usually doesn't work. Uh, so you just kind of want to put like up to face, and then click the bottom. If you don't have a face, then you would do the blind and specify your exact distance. Uh, some, like I said, SolidWorks isn't the best CAM software. There are definitely better. So some of these things aren't as smart as SolidWorks is sometimes. Some of these things aren't very smart, you know? So it won't auto recognize sometimes, or it will, and it will not recognize it correctly. Um, so in addition to like specifying your distance of that feature, you also have like your strategy to machine. Oh my God. Okay. Yeah, that was weird. Um, like I said, it's not very efficient. Um, you also have your strategy you want to take to machine this feature. So this is literally rough, rough, finish. So you're going to do two roughing maneuvers and then a finish pass. We don't really need that. This is a small hole. So we're going to just do rough and finish, which basically means we're going to do a rough pass to clear out as much material as we can, and then there's still gonna be a little bit of material, specifically like 10 thousandths of an inch all around, and we're gonna come back and just machine that gently. And what that's gonna do is, what the hell? Okay, I'll explain this a bit. What that's gonna do is leave a very nice surface finish. All right, a very precise and accurate surface finish, which is the whole point of CNC, is to get accuracy of complex parts. So what the reason why it like almost crashed my computer was because it was kind of trying to predict what tools to use to get this to work. So yeah, SolidWorks will do that. It's this partnership with Tech Database, um, where it's getting all these tools and materials from is like this giant online database. The only thing is, it's kind of bad and is not very good. So uh, yeah, you just kind of ignore it. Yeah, so we have our strategy selected. We have our distance of that feature properly selected. This kind of stuff is just like tapers and external profiles and things like that. So we're gonna, oh my god, it's doing it again. Dear Lord. See, like it just wants you to do what you don't want to do. Okay, so we're gonna check mark that. All right, so now here under our mill setup, we have our first little feature. So it's now that we have it like this, it's like, okay, this is something I can machine on this part. And like I said, SolidWorks can auto do this for you. It just will usually get it wrong. So it's better to show you guys how to do it manually. Because you'll probably end up having to go back and edit if you do it automatically. So we'll go back to mill setup part again, 2.5 axis feature. I'm going to start picking up the pace a little bit. So we're going to go to slot, which is right after pocket. We're going to select this face, and bam. See, you kind of recognize, all right, this is the top of that feature, this is the bottom feature. All right, yeah, I get what you're trying to say. End condition, and it still kind of did that blind thing. I don't know why it does that. But we're going to put up to face, bam, and it's all the way. See, it's kind of like fully modeling the whole thing. And we're going to say, yeah, okay. So now we have two, a circular pocket and an irregular slot. So let's get another slot going. So we're going to right click, 2.5 axis feature, slot is still selected. We're going to select this bottom face, and we're going to select like this face. Bam. See? So like I didn't have to do the whole profile, like the whole like contours. I just had to do one of the faces and it got it. So end condition. Shoot. See, it kind of popped that up. At least this time it didn't crash my computer. Um, we're gonna go up to face. And all these up to faces I could just specify blind, but I don't feel like trying to figure out what's this length again. Um, strategy. Yeah, we're just gonna do rough finish for everything. I should probably go back and change this one. So this irregular slot, I think I forgot to change it to rough and finish. Well, to edit it, all you do is right click on it, edit definition, and then see it's gonna pop you back up on the first screen. Oh, we don't want to change anything there, so we just go to end condition and see right here's the strategy. We're gonna switch it to rough finish. Well, bam, check mark. So we got three more features to specify, and they are of different types. So what we're going to do is come down to 2.5 axis feature, uh, just like the other ones. Then we're going to go with hole. And we're going to select two holes, that one and that one. We put end condition, strategy, drill. We're just going to drill them through. We're not going to ream thread or anything else. This general thrill will, like, you can put a bore maneuver or ream maneuver on it. This drill only is like you'll only be able to drill it. So we'll just leave it on drill. And like I said, I could just specify an absolute surface distance, or I could just put up to face and then click the bottom face. Check mark. So now we have circular pocket, irregular pocket, rectangular slot, or sorry, irregular slot, and hole group one. So it's like two holes, so it's a group. If you click this little plus arrow, see it's got hole one, hole two. Uh, we're gonna come down here again, 2.5 axis feature. And this thing is strange. So I am doing research. I had to make an injection mold, and one of the things you have to make is runners, and runners are usually like these half circles on the plate, and yeah, it won't really recognize these as anything. I tried like all of them, but I finally got something that made them work, and it's if you choose a open pocket, and if you have a sketch already made. So I kind of saved you the trouble of making that sketch. You can choose it like this. So the way these runners are made is you just come in with a ball end mill and you just like machine it. Just do little steps at a time, doing like that. It's not really any other way to make that. But SolidWorks CAM couldn't really figure out that this 3D surface was made like that. So with this uh, I'm sorry, not open pocket, open profile. Sorry. Make sure you change that. Yeah, they're like right there and right there. Make sure it's open profile. What this open profile does is it's basically just going to follow a sketch. So this is good. If you have something like this that it's not recognizing, you can just kind of force SolidWorks to be like, no, just follow this line. So this is usually a good brute force tactic, or if you have like some weird geometry and SolidWorks just isn't comprehending it. Uh, so then end condition, as you can see, it specifies from this whatever plane this line is on or the sketch. So that sketch is on this top plane. So what we need to do, this one we can't put up to face. There's no face there. Even if you put the cylinder, it'll just kind of like look at you funny. Um, so you gotta put blind, and that is a 1/4 inch ball mill. So it's gonna be half of a 1/4 inch, which is 0.125. I just hit enter. I didn't, but yeah. So like, if you click on it, open profile, see it'll show it all the way to the bottom. So that's what we want. So that's good. Did you guys get stuck on that? Are you following along?
I'm good.
All right, that's good. So then right click, 2.5 axis feature, and this is going to be the last one. But it's kind of the weirdest one. Uh, we're going to go with an engraved feature, and we're gonna just select these. So engraving text in SolidWorks, I haven't found like a foolproof way to do it, but really, it's really counterintuitive. But the point is, you can make us like the text using the text command in a sketch and then extrude it like this. Uh, and this is kind of how you'd go about trying to machine it automatically. There are like CNCs which have automatic protocols for machining text, engraving text like serial numbers. So you usually wouldn't even do that in the CAM software. It would be like a manual command you do at the CNC. So the end condition, so we have the engrave feature. We have the bottom of those letters selected. We're gonna go to the end thing, so it's kind of like projecting it outward. We don't really want that, so we're gonna go blind up to surface. We're gonna select this top surface and see it already kind of changed the depth to 25 thousandths. And it kind of already selected a tool. I'm gonna click OK. All right, so we've defined all of the features we want to machine on this part. We're almost halfway there. Um, so we have a circular pocket, an irregular slot, a rectangular slot, two holes, which are as one whole group. Uh, we have an open profile, which is this runner. And we have the engrave feature. So that's pretty good. Um, the next step is where things get fun. So we're going to start with this circular pocket. We're going to right click on it. And we're not going to hit 2.5 axis feature. We're going to hit 2.5 axis mill operation. All right. And then we're gonna go to rough mill. Bam. We click that, and now we're getting into trying to machine our part. And why isn't it loading? Then, I have a good PC, and then every time it's trying to be like I want it to be a good PC, it just doesn't. All right, we're here. Okay, so in this case, this is a rather small hole. Um, we're gonna rough it with the same tool we're gonna like finish it with. So in that case, it's gonna be tool number two, the flat end mill. The only thing is, tool number two, the flat end mill, isn't really long enough, but we'll select it right now. Tool number two, flat end mill. We have it selected. We click OK. All right, see, now it takes us to this little screen. Um, and in the screen, it shows us the profile of the tool. Now, that hole is an inch and a half deep, I think. And, excuse me, this cutting edge is only 75, 3/4 of an inch. What happens is, like, at least when SolidWorks is like rendering this for its preview, it kind of chokes up all the way to the cutting edge in the collet, which is like where your spindle is. Um, so it kind of messes up. Either way, this tool should be longer. So what we want to do is we want to change this flute length L2 to, I'm gonna select it, or you can just delete it. Just change it to 2 inches. Bam. Oh, damn. I hit enter. Yeah, whenever you hit enter, it'll close that. But if you need to open it up again, you can right click on it. See, we're on a different tab, by the way. See, now we're on the operations tree tab. Uh, so whenever we select a tool for a part, we'll like shift everything. It'll shift that like operation over to the operations tree. We can right click edit definition and see. Oh, I think this tool maxes out at 1 inch. Oh well, that's fine. Um, like I said, this is just for like quick adjustments. If you want, you can go and define your own tool. I'm not going to cover that right now though. Uh, you can go define your own tool and you can like make like a crazy tool. Uh, you can do tapers and stuff. Those are like tapered end mills. Uh, but yeah, so see tapered, necked, um, that kind of stuff. But this is for the non-cutting portion or the yeah, the where it grips the collet grips it. Forgot the shank there. Uh, Properties hand of cut. That just means if it's a left-handed or right-handed helix. The tool material. All of the SolidWorks defaults are carbide, which remember I mentioned the surface feet per minute. Something I forgot to mention is it also changes with the kind of cutter you're using. The material of your cutter has a very heavy influence on the surface feet material per minute of the uh, of the operation. So it's not only the material you're cutting, but what you're cutting that material with that will determine your surface feet per minute. So carbide is what's used a lot in industry. It can cut pretty much anything, with the exception of exotic alloys and uh, yeah, just pretty much exotic alloys and ceramics. Um it is really good. It's good if you have the chance to use carbide. Use it. It's also very expensive. They're usually like 10 times more expensive than regular high-speed tooling, especially if it's like a specialty tool that's not like common. But uh, this carbide, it can machine a lot faster. So what SolidWorks will do is it'll be putting a lot faster numbers than you would machine. So say if we were machining with high-speed steel tooling, like this exact same tool, but high-speed steel, our surface feet per minute would need to be a lot less than this carbide. But for now, we're going to assume that we just have carbide tools. And I'll show you in a bit how to change that surface feet per minute so that like if in the event you're like this and you just don't want to define your own tool as high-speed steel, you can just override this carbide setting and like machine it the way it should be machined. So yeah, we're just gonna ignore that. We do want to change this right here. This comment on the bottom is the name of our tool, and when we spit out our code, it's going to say the name of our tool basically every time we do a tool change. So 1/4 inch carbide. See right here, CRB. Let's change that to like, well, you could change it to HSS, like for high speed steel, which is like the most standard tooling thing. It's perfectly fine for aluminum and even mild steels. But uh, we'll leave it as carbide, I guess, because I just said we're gonna stick with carbide. But the point is, you can change the name of the tool there and like its specifications, and that's just a comment. It doesn't change anything. It's gonna say that in the code. So whoever's manning your machine is gonna see that comment, kind of thing. So mill holder, you don't really mess with this. It's just how it's rendering. See, when it's rendering the cut, when we're watching that preview, it's gonna be holding it like this. Tool crib, it's the tool crib. This is the same as that other menu. Um, and station. So this is like what tool number it is. So if you need to change the tool number, you can change it here. Um, if you have a tool that's numbered 0, make sure you change it to a number because there's no such thing as tool 0 um, in a CNC machine. So like if say this drill was tool 0, we need to change it to tool 1. But if there's already a tool 1, then we just like put it as tool 7. And what these numbers correspond to is like slots in the automatic tool changer of the CNC machine. So you'd put these tools in those slots and you'd register their heights in the CNC machine with respect to each tool. And it'll kind of remember those heights so that when you go to machine, it'll just automatically compensate for different lengths of tools. So, and that's actually a G43 command. Uh, we'll get into, well, I mean, I'm not going to go over G codes, but I'll just mention some important ones. But yeah, all right. So everything there is pretty good. We just want to change the length of that length of cut. I'm sorry. And that's pretty good. So that's good. As you can see, this menu we're in, this operation parameters, it's like a menu within a menu. So right now we're in the tool tab and we're in the mill tool thing. Let's click over here and this F/S, guess what it is? It's feed and speeds, ooh, which is the machinist term for the surface, like the spindle speed and the feed rate of your operation. So if we look here, look at that, surface feet per minute. What did I tell you? And it's 785. That's eh. So the recommended for carbide on 6061T6 is anywhere between 800 and 1300 surface feet per minute. As you can see, it's already calculated the spindle speed for us, which in turn it used into the feed rate, which is right here, and it's even got two separate feed rates for X, Y, and Z. Um, and this feed rate per tooth is just right here. And as you can see, it's defined right now by the library, which is like its automatic tool settings. But if you just click this drop down arrow, you can hit operation and bam, see it opens it all up. So we can change the surface feet per minute right here. Instead of uh, this, we'll put it at 900. We hit enter. Oh, goddamn. Yeah, it closes it every time you hit enter. So just remember that. Um, it didn't change it then. 900. If you click off of it, it just won't change. What the hell? Um, yeah, or you can define it by the tool, which is specific to that whole tool thing we were editing. Well, it dropped it. 800. It just doesn't want to change, man. Sometimes SolidWorks really do be like that. I think I know why. So remember we set our machine as medium duty. It, like I said, it sets maximums and minimums for the machine. So it kind of just won't go over this value because we have our machine set at medium duty. If we want it to go any faster, we'd have to specify that our machine is high, like heavy duty. But we can change the feed rate. So right now it's at 21 thousandths or 21 ten thousandths of a inch, and that's the this feed per tooth is the chip load. This is the size of each chip that's going to come off. We can just change that to a flat 3, and let's look at that feed rate, these feed rates right here. We hit enter. God damn it. Man, I always forget that. All right, see, it's at point 0.3, and these numbers changed. This was at like 56 before, and now it's 72. So, very nice. So that's 3 thousandths of an inch. We go to roughing, and these, this is basically the pattern the cutter will follow when we're machining. So we have pocket in, which basically means it's going to be cutting the same shape. Um, it's going to cut it once in the center, and it's going to go a little further out and twice, and a little further out and 3. What this kind of does is it'll kind of just like jump into the side wall that it's cutting right now. This usually kind of like when you're hearing it machine, it's like we're just kind of making that punch into the side of the wall. So it's usually like like it's not that good. You're putting a lot of instantaneous stress on the tool. You're increasing the area in which it's in contact with, and what you want to do is like minimize the area the tool's in contact with. This prevents you from breaking end mills. So uh, it's not good for that because you'll just dive right into that sidewall, and then like you just have like this whole curved surface it's cutting against, and you kind of just want to minimize that to like a little flat line it's cutting against. um, so pocket in or pocket out, which they're just the reverse of each other, they kind of do that, and so we don't really want to do that. Zigzag is just gonna, or sorry, this is zig, which means it's gonna cut in one direction, and zigzag is it's gonna like double back on itself like that. Spiral in, so it's gonna go from the outside and slowly way in. This is basically a better version of pocket in. Uh, it's pocket in, but without that sharp jump. Um, so it's just gonna kind of even out that jump just by like doing a steady spiral. And then likewise, there's spiral out. There's plunge rough, which is this. It's just going to keep jumping and cutting it out. And then there's offset rough, which is this is like it's going to come in from one side and like follow the same path. And then there's the special one, volume mill. All right, so this is like what this volume mill is this is a special patented program designed for high speed like high production rate machining. So this is commonly used in not specifically volume mill TM. There's other versions of it. Mastercam has like their own version of this, and I forgot what it's called, but it's not called volume mill. This is the one SolidWorks is using. But it's what it is it's like this weird contoured, like bubbly machining surface that's like generated by this complex algorithm. And what it does is it's like, how fast can I machine this thing while like putting a constant load and not just destroying the part or the tool for that matter. And so you get these like really uh, like really bubbly curved surfaces where it's kind of cutting like in this um and so this is like very high production parts, they make them like this. So uh say for instance you need a fixture and you're CNCing it, why do zigzag, which takes let's say it takes 2 minutes to cut like this face in zigzag. You could do this volume mill. I just keep hitting no because I don't want it to try and start rendering itself already. You could do this volume mill, which instead of taking like a little cuts and zigzagging it, it's going to take a one massive cut and just like do this really unique curved cutting thing where it's constantly in motion, constantly cutting, and then you end up reducing that 2 minute cut time to like 1 minute, like, or 1 minute 30, something like that. So it's really just for increasing the rate at which it machines, and more so than that, it tries to take as large cuts as possible. So what you do is you engage more of the cutting, the length of cut, and what that does is it like distributes the wear of the tool more evenly. So you're not just like wearing out the edge a whole bunch, you're wearing out like the entire side of the cutting tool. Uh, so that helps like keeping your tools uniform instead of getting like a rounded edge at the bottom. And so for this one, I'm just gonna like spiral out. So because we're gonna drill in from the center and then spiral it out a little bit. Our cutting tool's like pretty big compared to this hole, so it's not gonna machine much. Sorry, yeah. So that was just a brief explanation of all of these. So we're gonna choose spiral out, the minimum diameter, which is like that little inside diameter. It's let's see, our cutting tool is like already a quarter of an inch. So yeah, that's fine. That's 25 thousandths. It's perfect. So the allowance, this is how much space it's going to have off the wall. See, we're in side parameters. Allowance, 10 thousandths is usually what you want if you want to come back and do a finish pass, which we want to do. All of our operations will have that finish pass except for that, this and the engrave and the holes. Uh, so this 10 thousandths, it leaves that extra. And what that does is it's just like a nice amount of material for the cutter to come back and remove to leave a very nice surface finish. So 10 thousandths is the default. This step over is like how much is it gonna like jump over to the next one. So you may think like, oh, well, we already specified that in the feed rate. No, well, the feed rate is just how fast it's gonna go. Uh, that is dependent on like our step over, kind of. Um, what it means is just how much of a percentage of your cutter width are you going to go between like the next path, the next spiral in this case. 40% is fine. When you're working with harder materials, you're going to want to take smaller step overs. And what this will do is remember the whole the area of the cutter you're engaging kind of thing. Uh, like if you're wait, we didn't want to do the pocket out because it was going to just like ram itself into the side of the wall and like make that huge area it's going to engage. This step over is basically also that area it's going to engage. So is it going to cut like just a little edge, like a little tiny side surface of the circle, or is it going to cut like half of the circle? In this case, it's going to be cutting 40% of the circle area. You kind of get that. um, Resting machine, here's the cut method, climb or conventional. We're just going to leave them all on climb, but see what I kind of mentioned earlier. And then depth parameter methods. Uh, what this is just how deep you want each cut to be. In this case, like the first cut's going to be 50% of the depth. This is all relative to the cutter tool. So our cutter tool diameter is a quarter inch. So if I click off percent, see 50%, half of a quarter is 0.25. So you can specify as a number or you can just specify as a percent. First amount and then final amount. So it's like a finishing pass we have here of 10 thousandths, same as our side allowance. And that's pretty good. It's just we're going to have like an extra finishing pass at the bottom. This method equal, usually you want to keep it there. It just tries to even out the cuts as much as possible. And so you have your first cut amount, which is just like the first cut it's going to do. And then you have your max cut amount. And so what this is specifying is the maximum for everything the um, after the first cut and before the last cut, because we have a final cut amount specified as well. So, and this is just a maximum. So they're they can at most be that number, which is 0.125. But that they'll probably be less because it's gonna like try to stick two in there, and then like it'll do one that's 0.125, and then the other one, because of this whole like 10 thousandths off the bottom, it'll be like 0.115 kind of thing. So there's that. Usually that's what you want to stick with. These are like more complex things. Let's not mess with them. NC, this is I forgot what NC stands for, but the point is this is where you turn off compensation. This is pretty much the CNC's compensating already because your cutter's a certain diameter. If you want to get rid of that, which we do in one of the later operations, uh, you just click that off. Feature options. Well, this is a circular pocket kind of thing. The drill method, the entry method right here. Features options entry method. We want to change this to spiral. And so what it was before was plunge, and that just means it's gonna take the cutter and just drop straight to the depth you need. That is, of course, at a specific feed rate, but it's just gonna pretty much go straight into the part. This like puts a lot of wear on end mills specifically, which we're using. So we don't want to do that. There's entry drill. So it's like if you want to come in and if you there's a pre-drill in the part, it'll kind of follow that drill. Uh, there's ramp, which is pretty much just gonna like still going straight into the part, but now like following a kind of like little going to the to the side at the same time. This helps with the like it's better than plunge, but it's the best one is spiral. So it's gonna be doing like a little helix down. This is like the best thing for getting into with a flat end mill. Um, Anything else? There's like entry holes as well. There's ramp on the lead, and this is just like if there's already kind of a ramp there. Um, so we want spiral and the pitch. This is how pretty much the pitch of the helix, the between each revolution of the helix, how far down is it gonna go? Um, so 10 thousandths is fine. I'm sorry, that's a tenth of an inch. The radius of the helix. This is pretty like this is the radius of the helix. How large of a circle is it going to be rotating the cutter to make that helix? Let's take that down to half of that size, so 50 thousandths or zero point 0.5. And then I don't want to exit it, so I'm just going to click off of it. Um, sorry, whole center. Leave everything else the way it was. This is just kind of like extra stuff for rapid planes and stuff where the tool can move as fast as possible because it's not cutting. Advanced, this is again Z limits because of, like I said, the whole rapid planes and stuff. Posting, we don't care. This is like specific to optimization. We're not going to mess with any of this stuff, but this is like SolidWorks tries to figure out, okay, what's the fastest way to do these things? And you can kind of manually take control of that here. All right, so that was kind of long, I know, to explain all this, but so we have our first operation kind of set up. And so now that we have that, we can right click and we can click generate toolpath. So we set up all of the parameters for everything we want to do. We specified the method we want to go into it, how it was going to go into it, with what tool. And now we hit generate toolpath and should have already generated it. Yeah. So usually it does it pretty quick. It's literally just making like kind of a text file whenever you do that. But now that we have that made, what the hell? Why didn't it? Damn, really do be like that. So sometimes like you'll hit generate toolpath, but it just won't change it. When it's blue like this, it means it hasn't generated the toolpath. Uh, Even though you hit generate toolpath, um, sometimes it just do that. I haven't really figured out point. It's weird because when you export it, it'll like generate the toolpath. It'll be on the file you export, but it won't like show here. So I can't simulate it because it's saying that, oh, there's no toolpath. So what we'll do is we'll go on to the next feature, uh, do this, and it should like the next feature should say it and it should come out. All right. So we go back to the solid CAM feature tree. the irregular slot, we're going to right click it, not 2.5 axis feature, but 2.5 axis mill operation. Actually, I'm sorry, man. We're going to right click uh, again the circular pocket because that was our rough pass. We're going to go for a contour mill. And what this is going to be is our finishing pass. So we want the same tool. Yeah. And we already changed the tool. We don't need that. These feeds and speeds are fine. We could change the tooth, but I already showed you how to do it. The allowance is going to be 0. This is our finishing pass. So this is like, we're going to take it to the final diameter we want for that part. So the allowance should be 0 on the side and 0. So sometimes when you're doing these finishing paths, like I said, you're usually using you're using a different end mill, and it may be very delicate if it's a very fine end mill. Uh, you don't want to touch the bottom because, like I said, you want to engage as little as the cutter as possible. So you're putting as little strain as possible on the cutter, and so you might not want to put it all the way to 0 because what that'll do is you're not only engaging like the side of the cutter where it's cutting, you're also touching the bottom. And so now you have that extra stress of the cutter touching the bottom, which you don't even really want to machine, but it's still touching it, and the side. And I've broken end mills by doing that. So sometimes you want to, uh, you don't specify that here. That's in C, that's rapid plane, lead in right here. So, got limits from top of feature. Oh, no, was it on? Man, I'm getting tripped up. Damn. Yeah, man. I just got tripped up. I don't remember where it is now. Yeah, so sometimes you'll want to like specify not to go to depth, and I can't remember how to do that. I think it's here. First cut from now, that's for first cut. Uh, the lower limit. There's an easier way to do this without having to like specify an absolute Z lower limit. We'll come back to that, but keep that in mind. Uh, that you don't want to go sometimes. Like if you're using the same cutter, like in this case, it doesn't matter because you already know that cutter can do the full bottom like that and the sides because you just did it to rough it right now. But if you're using a very fine end mill, you want to like not break that end mill because they're usually very expensive as well. So you usually want to like kind of get that gap there. Like say leave that bottom Z allowance, but the side allowance is perfectly fine. Should be here on depth parameters. Actually, oh, here it is, allowance. It's right in front of me. So you could say, like, oh, I want to leave a 1,000th of an inch allowance on the bottom. We're not. We're not. We're just going to say 0. No, go all the way. But there's where you change a bottom depth allowance. And so, see, we have our contour specified. We have that. We need to change the lead in. So what this lead in is pretty much when the tool's inside of here, instead of just like all the way around, it's first got to like come into contact with this side face. So right here, it's going to like come in, it's going to do a little arc to kind of like curve into the final uh, distance, and then it's going to keep doing the circle. Uh, I don't know. There's sometimes you want to put none because usually sometimes when it generates these, it'll be like colliding with a part you don't want to machine, and so that's a big problem. You're going to be machining material you don't want to machine. So you can change that instead of like the side arc lead in, you can change it to like perpendicular. It's going to be straight into the part. Parallel, it's going to come in like almost in line with the part. Or you can have none. Like it's just going to get to depth and start machining. Um, so we'll do perpendicular because we're dealing with like a sidewall. Um, yes. You can change it, usually the lead out, which is pretty much the same thing. It's just gonna like do it opposite way when it finished that cut. Uh, it's usually the same as the lead in, but you can specify it as something else if you wanted. And that's pretty much it. So this one, this lead in is special to contour cuts. So this wasn't on the other one because the other one was a rough, but this is contour. So bam. Uh, Entry method, usually with a contour, it's none because you already roughed the hole. So usually it's none. Uh, and that's pretty much it. So we'll click OK. And see, now we have this contour on our operation tree. We can right click it, generate toolpath, and see it generated this one. Still not generating this one for some reason. Yeah, so like I said, it's not the best software, but it's what we have to work with. So we simulate the toolpath. I'm sorry, that was right here. Solidworks CAM, simulate toolpath right here. Um, Click run. See, so it didn't render the rough, but it is rendering the the contour. So see, there's the contour. It's just coming in and then doing that. Most of that material should already be cleared out because we have the rough operation, but it's not rendering that. So kind of sad. But there we have it. We have our first two operations, and we have this hole, this little pocket already finished. So I'm going to try and pick up the pace because I know this is getting kind of long. Um, but it is a lot to take in. It took me a long time to figure this stuff out. But let's get into it. So we're back on the CAM feature tree. Let's start with this irregular slot, the wave form kind of thing. That's 2.5 axis mill operation. We're going to rough mill. And for that one, we're going to use the half inch. This one, tool T4, the tool 4, half inch. We're going to check mark it. And like that one, we're going to change the length of cut to 2 inches. We're going to change it to a 2 inch length of cut. All right. And then we'll change this overall length to 4 inches. And what this does is like the flute length is still 2 inches, but we want to have 2 inches also for the shank. Number of flutes, two, straight, everything else the same. Mill holder, tool crib station, all that stays the same. So, excuse me. Feeds and speeds. Library has it at 811. I think this one will let me change it. So, right now the spindle speed is 1600. That's kind of slow for aluminum. Let's put the surface feet per minute at 1,000. And bam, it picked it up. That's still kind of low. 1200. All right, I can live with that. Uh, let's change this to, screw it, we're roughing, man, and we're gonna go fast. So 5 thousandths of an inch. Well, bam, very fast roughing. Now this one, we could zigzag it and stuff like that, but let's use that volume mill. No, this may or may not crash your computer. All right, so you say yes, it's going to pop up this separate menu for the volume mill. And so it has these general material classifications uh, where we are using aluminum, so we're going to leave it at that. But specific to that, you could specify the hardness of your material in Rockwell C or B or Brunel. We'll leave it at its default because I don't know the Rockwell hardness of or Brunel's hardness for that matter of 1061. Coating, this is the coating of your tool. We're going to assume we have uncoated tools. Basically means they're not like titanium nitride coated, the gold coating, or aluminum titanium nitride, which is the gray coating. Uh, Part holder, we'll just say it's good. Like we have good holding on the part. Machine taper. So there's standard tapers for machines in the US, we use Morse tapers, which come in 30, 40, and 50 sizes. It's basically just how big is the collet or the tool holder for the machine. And then there's specific types of tool holders. So you have a shrink fit, which is like you freeze your tool and put it in there, and it shrinks onto your tool holder. It's hydraulic chuck, milling chuck. These are collets, which are like little metal spring kind of things that you stick your tool in, and then when you tighten them, they grip your tool. And then there's a classic end mill holder, which has like a hex key to hold your tool. And then you can go from conservative to aggressive. We'll keep it at conservative. Um, that's just like how hard is it going to go machining? How deep are the cuts going to be? We hit OK, and then we hit preview down here. So you can hit preview here anytime to see how like it's going to look when it spits out the code. Uh, we hit preview and see it's going to give us this little thing to like, okay, like I'm going to, this process manager is pretty much saying like we're going to render that volume mill you want to do. Or wasn't it? I'm sorry, you guys select the rough mill. There you go. The hell wasn't working? No. Or is it running right now? Okay, there. It was running. Sorry. Yeah, it's a little weird. And bam, there's our volume mill generated. That's kind of weird. Uh, so yeah. So for some reason, it's still should have attacked from the sides. Just go from the sides instead of spiraling in. Well, it spiraled in. Roughing step over. We're just leaving that 10,000 allowance. Step over 40%. That's good. See, like I said, big cuts. We were going what, half of the depth of our cut for this hole, and now we're going 200%. So double the depth of cut for this volume mill. So it goes big. It doesn't go home. Climb, everything else. That's fine. I guess I would just I need to pick up the pace. So that's good, man. That's good. I like that. And see, because the volume mill had to like render itself, and we previewed it, it already like generated the toolpath for this one. So if we simulate toolpath and we hit go, it's going to show that one first. Yeah, yeah, it's kind of boring. And then it's going to, it's actually pretty slow. Oh, it's really slow. So you can speed it up. Should speed up right after it gets to depth. Oh yeah, it's speeding up. So you may think this is slow, but it's taking such a big cut that it's pretty fast compared to like the other methods. Because the other methods would have broken this up into like much smaller layers, or you would have had to because they're very rigid machining methods. But it's kind of weird. They normally attacks from the side, and I'm not sure why it's doing that now. Anyways, let's keep moving. So we'll do the finishing pass for that same rectangular slot. So 2.5 axis, I'm sorry, on the irregular slot. 2.5 axis mill operation, contour mill. We'll use the same cutter, the 1/2 inch cutter. Check mark. Yeah, that's all good. That's good, man. That's good. So we'll say okay. See, once you have like your thing specified, you can just, start doing that. We'll leave the lead-ins as they are. Um, we'll do the next one, which is the rectangular slot. 2.5 axis mill operation. We're going to rough it. And we're going to use the tool 3 and 3/8. Check mark that. We're not going to do the the volume mill, because I tried that one time and it was kind of weird. It it just it didn't understand what it was trying to do, and it kept rendering wrong. So we'll just zigzag it. So this one, the step overs are very important. They're going to be very rigid step overs. The cut amounts are much smaller. You can change that, of course. I'm going to leave it climb. Feeds and speeds. Feeds actually kind of low. I'd we'll change that. Change that to 1,000. Damn, I press enter. Uh, yeah, so that's 10,000 RPM. We'll change the chip load to 3,000 7-inch. Put preview. No, kind of like generated already. Look at that. Look at that. Ain't that nice? Uh, hmm. Drill method. Same thing as last time. Spiral it. Pitch, 1/10 of an inch is a little steep. Actually, no, let's leave it at 1/10 of an inch. That's pretty. I meant the radius. 1/10 of an inch was kind of steep. Uh, change that to 1/2 of a 1/10 of an inch. Yeah, perfect. All right, we'll put OK. And see, you can kind of see it's gonna spiral in right there. It's gonna like do all that, and then it's gonna spiral in right here and do the circles. It'll spiral in right there and do that, and spiral in again right there. It's a little weird toolpath, but it do that. Then this next one, the whole group, we're gonna put. See, its options are different than the other ones. It doesn't have like 2.5 axis mill operations. You right click on it, and it has whole machine operations. And so we're just going to straight drill it. But there's all the other ones too. And look, rough and contour mill are there too. We're just going to go straight drill. It's already got our drill selected. That's perfect. Drill hole parameters, side peck, mount. So the type pecking, it just means it's going to take a little, like it's just going to go in a little bit and then back out and then back, go in more, back out, go in more, back out, go in more, back out until it reaches the depth. You can specify the first peck's going to be like that, and then the last one, and then dwell. It's like how extra it's going to go or how long it's going to stay there. There's high speed pecking, there's variable pecking, there's gun drilling, which is just like different kinds of styles of doing it. And then there's straight drilling. So you want to use this if you have like the special CNC drills, but if you're using a regular drill, you usually just use pecking. If you have a very special CNC drill, which are called spot drills, it's actually better to just go like straight into the part, because if not, it kind of messes with the edges of the drill. But we'll keep it at pecking. Like I said, everything's kind of preset with pecking. You can change the surface feet, which will change the feed rate into the part and the spindle speed, but usually it's kind of auto optimized. You have to like see it uh, when it's machining, and like I said, when you render it, it's literally just a straight line down, straight line down. Even though it's pecking and it's like doubling back on itself, it just makes a straight line because it's just going through the hole. All right, that's beautiful. So see, we're getting our operations here. Now we're on the open profile. This one will be straightforward. Instead of it doesn't have a rough mill because it's following a line. It kind of gets like, okay, I can only contour this. I can only contour this line. So we just hit. So we just hit contour mill, and we're going to choose our 1/4 inch ball nose, which is tool number 6. We hit that check mark. There's some very important things we want to do here. First of all, this is just specific to the fact that we're machining aluminum. We want to take very small steps, or else we will melt it. Doesn't matter how slow we go, like we will melt it unless we take very small steps. So let's change these steps instead. We're gonna go down 0.25. It's kind of nice to like go down even increments to the final thing. Uh, but we're gonna go down 0.25. So you can do this in like 50 thousandths. Oh shit, that's 5 thousandths. And 12.5 is not divisible by many things. Uh, you can do like, I don't know, 10,000 steps. So like our first cut will be 10 thousandths. And this is like very conservative, but like it's very easy to melt aluminum with the ball end mill. I'm just telling you now. So we'll do 10,000 steps, and that doesn't add perfectly to 25 thousandths. So like our final pass will be a 5 thousandths pass. So it's gonna take a little while. It's gonna be doing that quite a few times. It's gonna be doing it like 13 times, but it'll give us a nice finish. At least it should. Feeds and speeds, we could lower the feed and the speed. The speed's very high, which it should be. It's a ball end mill. They need to be very high on aluminum, but it's that same high speed that gives you a nice cut that can also melt the aluminum. So feed per tooth, we could change this and make it like maybe a little slower of a progression, but that also increases the risk of melting. And allowance 0. Now, something very important to change if you're doing this open profile method for runners like this, or like these little circular semicircle slots, is you have to go over to NC and you have to turn off CNC compensation and say without compensation. And so what this does is pretty much right now, and for all of the other operations except for the drill, our code was adjusting for the width of the cutter. So the coordinates you see in the G code are the center of your cutter, the exact center of where your cutter is going to be. We're compensating like from the edge of where we cut because of like the radius of our tool. You get me? Like we're not really cutting at the center of our spindle. We're cutting at the radius of the tool. So it automatically does that. And like not only that, but CNC machines with their own special functions, like the machine itself, not the programming we're doing here, can adjust as well, like on their own. So what we're doing here is we're saying no, don't do that. Don't allow the CNC machine, to do that either. And what that's going to do is it's going to put the center of our tool right on the center of that line we drew, which is in the middle of our little slot, and that's going to allow it to cut it the way we want. If not, it would cut it like literally half on this line and the other half on this line. Like it would be doubling back on itself, and it would cut everything but where we wanted it to cut, pretty much. Um, and so that's just for this particular case where the line's in the middle and you want the runner to be in the middle. Um, and that doesn't just apply to ball end mills. You can do it with other end mills too. Uh, if you have that path and you just want to follow exactly that path, not be offset by the cutter. So we make sure that we have that off. In this case, the lead in this case, we don't want it to lead in because it would be cutting this material on this flat face. So we put none. So it's just going to go straight into the part, which is fine. So it'll go straight in and then it'll follow that line. So that's very good. Advanced, we don't need that. Optimizing, we don't need. Contour, everything's good. So we say preview and see it just cuts that up into like 13 steps. Bam, 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 bam. Again, that's kind of a very conservative, uh, but it's fine for this demonstration. So how are you guys doing? I haven't asked you. Are you guys following along? Is it making sense? I know this is taking quite a while.
I'm following. Yeah.
All right, yeah, it's I'm trying to blend like the actual machining know-how with like this programming side of it because they're two different things that need to go hand in hand. Uh, so a little machining wisdom, you can and will melt aluminum with ball end mills. With the you need to like turn off compensation or else it won't be centered. Uh, wisdom. So we're on our final thing, the engraved feature. This will almost never come out the way you want it to. So 2.5 axis mill operation, contour mill. And we're going to choose that 1/16 inch end mill. Look how tiny it is. It's tiny. All right. We'll just click yeah. Uh, yeah, that's fine. Uh, look at that. The surface feet per minute is so low and the spindle speed is so high just because of how small the cutter is. Uh, it's funny. Um, the cut amount, ideally you want it to like just do it all in one pass. So you might be able to do that. But oh well, you could specify the first cut to RAB to depth, and then it would just kind of like negate the final cut and the max cut value. Uh, which we can do. No. So other than that, I would just turn lead in off. Same reason as why we turned it off here for this runner, because if it leads in, it's going to be cutting material that we don't want to cut. So we turn off lead in, advanced posting, and that. Let's preview it and see. So the way SolidWorks is like interpreting this is it's going to follow the outline of the letters. You see that? Like that blue line is pretty much the toolpath. And then this green line is where the tool is rapiding, which is basically it's moving as fast as it can because it's not cutting. So it's coming down. And it makes this A. It ends up back where it starts. So it gets up, goes over here, starts the S, ends up back where it started, goes over here, starts the M, ends up back where it started. Yeah. So yeah. So this is really the only way to like engrave text is to like have it do it twice, not like follow the middle. Um, this is the engraved feature. If you want to like get technical, you could do an open profile, draw the letters in a sketch, and then have it follow that profile like we did here. Um, but that being said, there are CNCs that have their own built-in functions. So, for instance, Haas machines, if you put a G47, you can engrave serial numbers and sequential serial numbers at that, and it will like engrave them like a normal engraving, just a simple line letters, not doubling the letter, not following the outline of the letter. I mean, so there's multiple ways to do these kinds of engraving, uh, but this is just like the regular engraving, the engraving function, at least on text that's been debossed into a part. So yeah, wait, let me try something with this first one, edit definition. And if I hit preview, oh, it's still not rendering it for some reason. Yeah, I'm not sure. Might have to look into that. But yeah, uh, we just finished programming this part pretty much, except for that one. It's still messing up. But we can simulate the toolpath. We can put it pretty fast because it's kind of long. Not if you put it all the way to the end, it's just kind of like and it's done. So it's a little weird. But yeah. You guys have any questions?
No, I'm good.
Yeah, I'm good too.
All right. Um, yeah, so it's a little confusing. It's a lot of menus, but once you get the hang of it, like you can start doing it pretty quick. Um, and like I said, SolidWorks isn't the best one out there, but
So which one do you recommend? What software?
so there's one called SolidCam, and I've heard it's like the best one out there. And actually, while we're on that subject, I'm gonna post a little link because one of our team members, like Miguel, he brought up like this YouTube channel that they do like CNC training, but it's like you gotta pay for it. Um, but they do like Mastercam tutorials, and so there's a lot better Mastercam tutorials than there are SolidWorks Cam tutorials. SolidWorks Cam is like a new thing. It was introduced in SolidWorks 2018. So it's really like it's new. It's doesn't have all the bells and whistles, and like they're still figuring out how to do it. But Mastercam's been around for a long time, and it's meant just for cam. It does have like a CAD aspect to it. You can design parts in it, but it's meant for cam. Uh, but yeah, so I put that link. If you go on their YouTube page, they have a bunch of videos of them just machining stuff. But if you search through those videos, you can find Mastercam tutorials, um, and they're pretty good. Like I saw them, and it was very straightforward, and they explained it well. And they're like an hour long. They have their own like parts that they do, kind of like this. Um, and like I said, a lot better. It's all the things that SolidWorks kept messing up on. It pretty much just has those fixed. Um, but yeah, it's uh, it's pretty good. There's a lot of software. The NX has its own version of this cam, and I kind of said like, oh, I'll like go out. I'll go on to like learn it so I could explain it like I did with SolidWorks here. Like I said, I'm showing SolidWorks. Uh,
The other software that they have something in common, right? They're kind of similar.
yeah, so Autodesk has their own cam. It's kind of weird. It's leaving that tab. That's weird. So like with this simulate, you can diagnose if it's gonna do what you want to. Like right now, it's not doing what we want it to, but you would change that by going back, changing some of the values, changing the lead in, maybe where it's approaching from, things like that. Uh, or maybe you might even have to go back and redefine the the feature. So we defined the feature a certain way. We chose this face, the curve face, and the bottom face. Maybe if we chose the curve face and the top face, it would change how it's machining. So, and I think that's just a SolidWorks thing. I think you can change that stuff a lot easier in other software like Mastercam. Um, but yeah, see, it left this tab and I left these tabs. So it shouldn't leave those tabs. But yeah, that you would go back and start changing things. And so that was a big thing of what I had to do. And it did that pretty well. So that's the zigzag thing. Yeah. Yeah, let's speed this up. Oh my god. Yeah, so it's machine through there. We probably should have made the tool longer. Making the tool longer in here just kind of helps with this like rendering because you set the tool height on the CNC. So you could say, oh, it's a 3-inch tool, but then when you're in this tool thing, you're actually like using the when you're at the CNC, you're specifying a tool height. So let's talk about that. So yeah, let's say like okay, that was perfect. It worked the way we wanted, even though it didn't. We would normally go back and change some values in here, mess with the tool paths. You would go to post process, which is here on the SolidWorks tab. You'd hit post process, and then it's gonna be like, oh, it's pretty much gonna be a save thing, and you're exporting it as a txt, and so you hit save, and then it pops up this menu, and you hit play, and it literally just generates your code, and bam, so it's done, and tells you the size of the file too. You can go to your files, and it should be there, right here. So let's look at this for a second. And it's literally a text file. So 00, uh, 0001, this is program one. Uh, these N numbers are like the line number. They don't really do anything. G20 is start program. And it's, remember that comment we put? So this is the name of the tool. G91, G28. This is like reset zeros, X0, Y0, Z0, like go back to zeros, basically, whatever you specified for the CNC. And then this is tool 2, M06. So M06 is tool change, and then tool 2 is tool 2. So it'll change to tool 2 if it's already in the spindle, depending on the brand you're using of CNC. It'll just kind of skip this. It'll say like, oh, it's already in the spindle, and go to the next one. So Fanucs will do that. I'm sorry, Fadals will like do that. Fanucs, they will have an error if you have the same spindle and you put like a spindle tool change. So like you have to know what CNC you're working with when you're writing this code and when you're editing it as well. The other thing with Fanucs is you have to put G49 in front of every uh, tool change like this. So right here you'd put like G, and you can just type here and save it, and it'll change the code. G49, and then you Control S, save it in front of all of the tool changes, because what the G49 is it gets rid of all offsets. So your tool, you set a tool length offset, right? Because your tool is a certain length and they're not all the same length. So you set that offset. What that does is it gets rid of the offset. So when it goes back to Z, it's like the way it should be. And it lines up the tool correctly. Fanucs will have an error if you don't put that G49 in front of every T0. And yeah, so it's there's little things, little ins and outs. Uh, G01 is like a depth, just go to that depth rapid. Um, yeah, each of these codes has like different specifications, things like that. But see, and then it's segmented into the different parts we want to do. Hmm. Yeah, it's not rendering that rough out here either. See, it's starting with the contour when it should start with that rough mill. See, so like you gotta like go back and diagnose. It's good practice to, even after like it looks good in that simulation, to go back here and like make sure it's good, make sure tool numbers are correct. And it is a long program, but just go for the main things. So like make sure, all right, yeah, that's the one that should be next. All right, these are just values it's navigating to after each cut. M30 is end program. So yeah, yeah, yeah. Well, I know it's been a while, but that's it, guys. Unless you have any other questions, that's kind of everything for the fundamentals of the SolidWorks CAM. Um, it's a lot of debugging. Uh, comes after your initial like make the program. What do you guys think?
It is a lot of information.
Yeah. So yeah, and as with CAM, the best way to learn it is to practice it, and unfortunately, you need a like $40,000 machine to practice it. Um, but yeah, like I mean, you can practice it with the little simulator. There's I think there's some free software that like is really good for simulating G code. So like you can spit out this file and then put this file in that software and it'll kind of like simulate how it's going to cut. But yeah, so that's it. You got any questions, Omar?
No, I'm good.
All right, man. All right, well, thank you for watching this video, and yeah.
Can you post the video later whenever you have time?
Yeah,
Larry?
so I'm gonna do that right now. So
Right.
yeah,
Well, thank you.
no problem.
Bye bye.
Yeah, thanks.